Hello, and welcome to this breakout session on confidential computing with SUSE and IBM zSystems. Next slide, please. My name is Jollans from IBM, and together with my colleague Mike Friesenegger from SUSE, we're going to take you through confidential computing and how it applies to the IBM zSystems running SUSE. Next slide, please. Security continues to be amongst the most important issues for CXOs. It became more challenging as computers moved out of the data center, and more challenging again with the emergence of the internet. And it's not just external threats. Internal threats through insiders stealing, deleting, or changing data are as big or greater a threat, and often harder to address because of the implied trust. IBM recently sponsored a study by the Ponemon Institute to look at the cost of insider threats. They interviewed over 900 IT and security practitioners at 200 organizations, defining insider threats as a careless or negligent employee or contractor, or a criminal or malicious insider, or a credential thief. They found in the study that the average cost of an insider threat was $11.5 million, and that 60% of these organizations had experienced more than 20 incidents per year. This is very scary stuff, especially if you consider that the insider threat has to succeed just once, but the security has to succeed every time. Next slide, please. The principle of designing systems for zero trust is also becoming widely adopted. It's centered on the assumption that organizations should not automatically trust anyone or any other system, either inside or outside the organization, but should instead continually verify. And that, rather than relying on promises by systems administrators or cloud service providers not to look to customers' data, it should be impossible technically for them to do so. To achieve this involves a combination of hardware, software, and processes. Next slide, please. There's three areas of data security that need to be considered: data at rest, data in transit, and data in use. Data at rest is typically static data on a storage device. Protecting it involves encryption combined with access controls. Often only the most sensitive data has been encrypted, which opens up many vulnerabilities. With recent progress in on-chip hardware coprocessors, has enabled the approach of pervasive encryption to become practical, encrypting all data by default. Data in transit is data that's being moved around, both across the internet and also within the data center. Again, encryption is key here, including using asymmetric cryptography and public-private key pairs. And finally, data in use, which is the data held in memory and being acted upon by the processor. Data is usually unencrypted for the time it is being processed by the application, and is so at its most vulnerable. Next slide, please. So how does IBM Z support security today? Physically, the IBM zSystems as a centralized system is easier to protect because it has a smaller surface area vulnerable to attacks, combined with robust access control. Looking at the top of the picture, each IBM zSystems processor, or PU, then has an on-chip cryptographic coprocessor, CPAC-F, which can provide hardware acceleration of symmetric cryptography, delivering much faster encryption and decryption of data at rest, and so enabling pervasive encryption to be practical. Moving down the diagram, the Crypto Express card performs two main functions: hardware acceleration for both asymmetric and symmetric cryptography, including new algorithms such as elliptic curve, and secure storage of crypto keys in a tamper-respondent hardware security module, or HSM. And finally, trusted key encryption provides a secure way of loading cryptographic keys and offers a safer alternative to clear key entry. So next slide, please. As you can see from this chart, The existing protections apply primarily today to data at rest and data in transit. Now let me hand over to my SUSE colleague Mike Friesenegger, who will describe in more detail how SUSE Linux Enterprise Server supports pervasive encryption on IBM zSystems. Mike, over to you.
Thank you, Adam. SUSE understands the importance of data security. Data is our customers' gold, which they use to drive their businesses. SUSE provides our customers the tools and technologies that can be used to protect our customers' gold. But SUSE does not do this alone. Rather, SUSE works closely with our partners like IBM to develop, test, and support these tools and technologies. SUSE Linux Enterprise Server has supported pervasive encryption for data in transit on IBM Z and Linux One for several years. The supported APIs include the library for IBM Cryptographic Architecture, better known as libica, which provides cryptographic functions for applications running on IBM Z and Linux One systems, both with and without cryptographic hardware. The second API is called Open Cryptoki for Linux on IBM Z or IBM Linux One. Applications that use this API can take advantage of the Enterprise PKCS and EP11 coprocessor mode of the IBM cryptographic coprocessors. Let's switch from data in transit to data at rest. When working with IBM Z and Linux One, all data is stored on storage arrays that are attached to the system via storage connections. Protected volume encryption, which is another name, guarantees the data is secure while it is sitting on a disk in the storage array, as well as when it is transferred from the storage via the SAN. A secure key is stored in the tamper-proof hardware security module of the Crypto Express adapter and used to derive a protected key. The protected key is used by the CPAC-F on-chip hardware encryption coprocessor to encrypt and decrypt the data at CPU speed. The latest versions of SLES, including 12SP5 and 15SP3, have important components that enable pervasive encryption for data volumes. The kernel modules PKey as well as PAES_S390X interact with the Crypto Express to derive the protected key. The dmcrypt module is used by the kernel for device mapper storage encryption and decryption. Crypt setup is part of LUX, also known as Linux Unified Key Setup, which is a Linux disk encryption specification. Protected volume encryption or pervasive encryption can use capabilities in LUX 2, the latest version of the LUX specification. zKey and zKey-Crypt Setup are tools from IBM. They work together to generate, validate, and re-encipher secure AES keys in conjunction with the hardware security module and used on volumes encrypted with LUX 2. Pervasive encryption can be done using SLES in an LPAR, a ZVM virtual guest, and a KVM virtual machine using DASD and fiber channel attached storage. SUSE extended the YAST partitioners to simplify the setup of pervasive encryption for data volumes. I'm using the text view of YAST in the next several slides, even though the GUI view will look very similar. This screenshot shows adding a LVM partition on DASDB. I have selected the encrypt device option, which is not a new feature in YAST. What is new is the pervasive volume encryption option under encryption method. The encryption password is actually the LUX passphrase, which is used and required to access the LUX header on the encrypted partition. The passphrase does not play any part in the encryption, but is used to unlock the LUX header. The available APQNs represent the cards and domains in the hardware security module, which are part of the Crypto Express adapter. The secure key must be the same on the selected cards and domains. In this example, All of the domains 1, 4, and 5 on card 1 are assigned to this VM, but only domains 1 and 4 contain the same secure key and are being selected. After selecting Next on the second screenshot, we see YAS setting up protected volume encryption on several partitions, placing the encrypted partitions in a volume group and logical volume, and finally formatting and mounting the logical volume. YAST also sets up /etc/crypt tab so that the partitions are automatically remounted on a reboot. YAST saves you time by not having to follow the very well-written IBM pervasive encryption documentation, as well as all the additional steps that are needed to set up LVM, formatting, and mounting. If you want to see this demo in action, I encourage you to watch the technical assurance for confidential computing using SLES on IBM Z and Linux One recording, using the link on this page, where I go into more detail about setting up pervasive encryption for data volumes using YAST. So Adam, what's next?
Well, Mike, what's next is protecting data in use. We've talked so far about data at rest and data in transit. The harder challenge, and the topic for the rest of this session, is protecting data in use. There's various possible ways of protecting data in use, but the leading one is based around data and applications being protected in an enclave by a combination of hardware and software, enabling the data to be held unencrypted in memory. And this is the area where which the industry is calling confidential computing. Next slide, please. It's probably helpful at this stage to clarify the terms being used. Confidential computing is the term used for the industry initiative, rather than for specific technology or products. Trusted Execution Environment, or TEE, is a term used for technologies used to deliver confidential computing. And IBM Secure Execution for Linux is a trusted execution environment which IBM has developed for the IBM zSystems and Linux One Enterprise servers, working in conjunction with our Linux partners such as SUSE. Next slide, please. To support the industry evolution of confidential computing, a range of hardware, software, and cloud vendors came together to form the Confidential Computing Consortium, which is a project and community hosted by the Linux Foundation with open governance and participation. The scope of the Confidential Computing Forum is to, quote, promote the widespread use of hardware-based trusted execution environments. Originally set up in October 2019, the Confidential Computing Consortium grew by 60% in its first 9 months alone. Confidential Computing Consortium has also written a number of white papers about confidential computing and held a developer summit last year. Next slide, please. Trusted execution environments have also started appearing on smartphones based on the ARM security extensions of TrustZone, and you may well already be familiar with the idea in this context. TEEs provide an isolated environment for applications to be securely processed on a mobile phone without exposure to the rest of the system, for example, to hold critical financial data. Next slide, please. So now we arrive at IBM Secure Execution for Linux, which provides a hardware-based trusted execution environment for IBM z16 and Linux 1.3 systems, working in conjunction with the Linux distributions such as SUSE Linux Enterprise server. Secure Execution provides a KVM-based virtual machine that's fully isolated and protected from the hypervisor, with encryption keys that only the IBM Z hardware and firmware have access to. It provides isolation between the KVM hosts and guests, helping protect against insider threats such as malicious administrators, while allowing honest administrators to manage and deploy workloads. You may remember an earlier technology called IBM Secure Service Containers, which provided a trusted execution environment at an LPAR level. LPARs on IBM zSystems provide a firmware-based virtualization of zSystems or Linux One, but you can only have 85 LPARs at most on one system. IBM Secure Execution for Linux builds on this and takes it to the next level with isolation at scale, since KVM can then support hundreds or thousands of guest virtual machines. It can help and protect and isolate workloads both on-premises and in a hybrid cloud environment. Secure Execution for Linux is designed to deliver secure multi-tenant hosting on a single system, as well as supporting regulatory compliance by being able to show that data is isolated. Mike will now go into more detail about how SUSE Linux Enterprise Server supports secure boot and secure execution.
So, although Secure Boot is not associated with Secure Execution, Secure Boot focuses on an aspect of confidential computing. With Secure Boot, an organization is assured that the Z and Linux One system and operating system kernel have not been tampered with, and that the Linux kernel is coming from a trusted source. The trusted source for the SLES kernel is SUSE. The firmware in the IBM Z15, the new Z16, as well as Linux 1.3 systems will check the kernel. If the kernel is not signed or cannot be verified, then the LPAR and the operating system in that LPAR will not load, and the load will be canceled. Currently, Secure Execution is supported for LPAR-based operating system loads using a SCSI LUN where Linux is installed. The support for Secure Boot started with SLES 15 SP2 for IBM Z and Linux One. The link on this slide will take you to the IBM documentation to read more about Secure Boot. The first command in this screenshot shows that this is running on S390X architecture, which is an IBM Z or Linux One system. The second and third commands provide details about Secure Boot. We know that this is a newer IBM Z or Linux One system that supports Secure Boot when the has _ option is enabled. The LPAR was booted securely because the second option, secured, is also enabled. Searching the boot messages provided by dmessage also shows that this LPAR was booted securely and the Linux kernel boot signature was identified as SUSE Linux Enterprise. Now let's look at a screenshot of the HMC and specifically the load screen for the LPAR called Zebra Echo 1 Charlie or ZE1C. Notice the Enable Secure Boot for Linux checkbox is enabled. Also notice that the worldwide port name, also known as the WWN, and logical unit number or LUN are being used. This confirms that this LPAR is using a SCSI LUN for the operating system load. What you cannot see is that I disabled the Enable Secure Boot for Linux checkbox and clicked OK to continue the operating system load. In this final screenshot, you see that the secure option is disabled. The dmessage output also shows that the secure IPL has been disabled. These two facts confirm that this LPAR did not secure boot this time when the operating system load was done. So now let's switch our focus to secure execution. The secure execution documentation focuses on the efforts of two personas. One persona is the cloud provider or system provider that manages the system where multi-tenant secure execution workloads will be run. The other persona is the workload owner who has a critical workload. Both personas are responsible for performing certain tasks in preparation for running a secure execution workload. The provider or system owner has the following responsibilities. One, they have to manage one or more IBM Z15, Z16, or Linux 1.3 systems that support secure execution. Each system has a host key that has been built into the system during manufacturing. The provider must contain and share with the workload owner the public key, which is part of the host key document. And finally, secure execution must be enabled via the HMC or the service elements that are used to manage the systems. With secure execution enabled, the KVM LPAR must be started with the prot underscore vert kernel parameter. With this parameter enabled, a VM that is being started with the secure execution header will be managed by the ultravisor and run within the protected memory area that was created when the KVM host was started. Now, you may have said to yourself that I used a new term, ultravisor, which you may not be familiar with. The ultravisor in the context of secure execution is comprised of trusted firmware that makes use of the memory protection hardware in the newer IBM Z and Linux One systems. The workload owner is responsible for building the image. Part of the decision when building an image is choosing the appropriate SLUS version and the type of disk that will be used by the KVM guest. The SLUS version chosen depends on the application that will be running in the VM. QCOW2 is the default virtual disk format for KVM virtual machines, although FCP-attached LUNs and DASD can also be used for the operating system, as well as the application data. This diagram from the IBM documentation about secure execution provides a great starting point to explain the responsibilities of the workload owner. Like I said on the previous slide, the workload owner is responsible for building the secure execution image. This slide helps dive a bit deeper into the tasks of a workload owner. The first step is to prepare the image which contains the workload or application. This can be done using an image building tool like Kiwi or manual or both. I prefer the approach of treating the image as code, so my recommendation is to build using Kiwi. I think an important thing to point out is to separate the application from the OS disk. Doing so should make OS and application executable upgrades much easier, at least in theory. Because security of the workload and the workload data is paramount, encrypting the data and the OS disk are a must. The key used to encrypt the data disks can be securely included in the encrypted OS boot image. You may remember me talking about the host key document that the system provider has to share with the workload owner. The workload owner will verify the authenticity of the host key document. This proves to the workload owner that the chain of trust with the system provider and IBM is not broken and the data will not be compromised. With the guaranteed chain of trust, the workload owner creates the secure execution header using gen port IMG and the keys included in the verified host key document. The boot image key needs to be included in the secure execution header to unlock the OS disk and access to the data key. Finally, the secure execution image and data disks are sent to the machine provider along with the XML definition for the KVM virtual machine. The system provider will define the VM and start the secure execution image with the standard versh command. I was hoping to demonstrate some of the tasks of the workload owner in a demo, but the host key documents were not delivered in time for the demo. I'm working on building a secure execution demo and how-to guide. So in summary, there are three main areas of data security: data at rest, data in transit, and data in use, with the confidential computing focus addressing data in use. And with SUSE and IBM Z, you are well covered to address all three areas. Remember to check out the technical assurance for confidential computing using SLUS and IBM Z and Linux One demo if you're interested in seeing a recorded version of the demos. From Adam Jollans and me, Mike Friesenegger, thank you for your time, and we look forward to continuing the discussion about confidential computing with you.